Mark has been in the field. It's my great pleasure to introduce today's speaker, Mark Johnson from Brown University. One of the wonderful things about having Mark here is if you were at ACL and you went to a talk which was a little bit boring, now you have somebody to complain to since he's currently serving as the president of the organization. Mark has been in the field for quite a while. He did his PhD at Stanford under Stanley Peters with other luminaries, John Barwise and Fernando Pereira on his committee, and ever since he's been working at, as I would say, mainline grammatical formalisms and transformations of grammars, and in more recent years has successfully made the leap to stochasticizing all these grammar formalisms and
Yeah. So actually, this talk came about rather suddenly. I think it was only last week that I was emailing Jason about something completely different. And I said, well, perhaps I should come down and have a chat with you about tree transducers. And somehow I got roped into giving the talk here. I think somebody said, why don't you just simply give one of your old ACL talks? So that's basically actually what I've done here. This is, you can actually tell a fair bit. The original work was done jointly with my colleague Eugene Charniak at Brown, and we presented it at ACL in 2001. You can tell something else from this. This ITR number here is actually the number of a research grant which is joint with you guys at Hopkins. So a number of people here are actually involved on this. So I think that might be very interesting as well for you to hear about this work. So the first half of the talk is basically going over material that we covered in 2001. The second half is an attempt to try to fix up what I see as some of the deficiencies in that 2001 work with a more sophisticated model. And I'd be very interested to, which I haven't presented anywhere before, and I'll be interested to hear what you guys think about that. Okay, so the overall goal here is to develop techniques for applying parsing technology and in general deeper linguistic analysis to speech. And that's a fairly difficult thing to do. We're starting off here by making the problem considerably simpler by trying to apply this technology to transcribe speech. Even that, and that solves a lot of the difficulties, simplifies the problem way oversimplifies it. But even then, you still have problems dealing with speech errors. And so I'm going to tell you a little bit about the types of speech errors, and then a two-stage processing architecture that we've dealt with, which basically is identify the speech error and correct it, and then parse the corrected string. And then most of the talk is actually going to be about two different classifiers, two different methods for identifying and correcting a certain type of speech error. One which just basically uses a machine learning technique to try to identify words that have been repaired on a word-by-word basis. And then a second one which is a somewhat more ambitious and actually I hate to say it, as yet less successful technique that actually tries to come up with a generative model of speech repairs based on, of all things, tree adjoining grammars. Okay, all right, so the sorts of speech errors that you get to see in transcribed speech are as follows. You get to see things like filled pauses. These are the R's up here, and I think it's refreshing to see the support. You get to see a tremendous number of parentheticals, like the you know in but you know I was reading the other day. And then the things I'm going to focus on today are speech repairs, which are things like, why didn't she stay at home? Which is where you basically get to see almost like a little rough copy or repetition of part of the material. And then finally, there are just out and out ungrammatical constructions, and I wish I actually had something interesting to say about those. Unfortunately, I don't know of any systematic way of dealing with those. You'll actually see at the bottom of some of my slides citations to relevant work. So if any of you are interested in following up on any of this stuff, you would do extremely well by starting off in those places. Okay, so now I'm going to try to make an argument for why speech repairs ought to be of special interest. Well, first of all, at least if you're parsing from transcriptions, filled pauses and parentheticals are pretty easy to recognize, and they don't actually cause any great problems with modern parsers. The modern parsers actually seem to recognize them well, incorporate them into syntactic structure reasonably well. Speech repairs, and actually this is really a bit of a cop-out. Ungrammatical constructions, it's true, they're not necessarily fatal, but the sorts of things that people wind up saying can often be so bizarre that it's really difficult to imagine how one ought to be assigning a tree to them at all. So perhaps one reason why I think they're not such a problem for a statistical parser is because I don't have any idea whatsoever what the tree ought to be like for some of the things that people actually wind up saying. Okay, so in the switchboard corpus, which is of a transcribed speech, so I guess switchboard was originally a corpus of telephone conversations that was collected, I believe, at UPenn, is that right? You guys probably know far more about that than I do. It was transcribed, and then at least the guys at UPenn were responsible for tree banking it. And so here's here's a syntactic parse tree together with the sorts of annotations. And so the fact that the you get here is a speech repair that has been in fact repaired is indicated by sticking all of this material here underneath of an edited node up here like that. So that's the sort of tree. Now our syntactic parsers are in fact actually trained by taking trees like these, and they extract lots of information, the local trees and head-to-head dependencies and other things like that from these trees. So you might say, well, the first thing you'd say is, okay, why don't we just feed the parser the training trees from the switchboard, and maybe in fact it will learn how to assign these edited nodes correctly. Wouldn't that be great? Then we'd have really nothing extra to do. We'd just use our standard parsing technology. Well, unfortunately, if you just use the unadorned parser and training regime and feed it the switchboard corpus with all of the edited nodes in it, and then run the parser on the development section, you don't get to see any edited nodes whatsoever. That is, the parser itself doesn't directly posit any of these speech repair edited nodes. And presumably what's going on here is that the parser is based on context-free headed trees and head-to-head argument dependencies, and these repairs involve something really quite different. They seem to involve what I call context-sensitive rough copy dependencies. In other words, why didn't he and why didn't she is almost like a copy, and it just doesn't have the sort of tree structure that these parsers are specially designed to pull out. In fact, I'll make an argument that this is like a little context-sensitive construction sitting in here. The parsers are basically context-free, so it's maybe no surprise that they don't pull them out. And then this bit down here is saying that what you really want to do with a speech repair in general is try to see if you can identify the words which have been repaired and just simply excise them, and then if you can just interpret the remaining words, you've gone a long way towards interpreting the original sentence as a whole.
A quick question.
Right?
What would the parser do to why did he, why did she say? Typically, what would come out?
Something completely crazy. Probably would identify this as some sort of embedded clause or something like that. So here's the general framework in which we're thinking, is that start off with the speech transcripts. We then try to see if we can come up with a device that I'll be telling you about today which will identify and remove the speech repairs, parse the remaining words to give you the parsed speech transcripts. This is probably where you want to stop. However, if you want to actually have a parse produced of the full, all the words, including the repair, you could reinsert the edited words, and then if you wanted to evaluate the parser, you could do that. So the sort of model would look something as follows. If the input is something like, and you can get a system, you do standard part of speech tagging on it to get the next line. Then with edited detection, in effect, you put in these brackets in here saying this is a speech repair. Parse what's remaining.
Actually,
like
the
this.
other thing is the repair.
What's that?
Actually, the other thing is the repair. This thing is the thing which is being repaired.
Yes. In fact, actually, yes. That's technically, this is known as the reparandum, and this thing up here is known as the repair. In fact, I'll get a little bit more careful about that in just a tick. And then if you want to, you can reinsert the edited words. Okay, all right, so that's the intro. Now I want to tell you about two different methods for identifying these repairs, or these reparandums, actually. The first one, which I'll just go over, is a method which just basically uses a machine learner to learn the characteristics of words that are speech repair, that are reparanda, that are in a repair. So basically, I just use a bytag HMM tagger to tag each word with their part of speech. Then there's a feature detector which then runs over these words and parts of speech. Those features and their values are then fed into a classifier. It's one. When I did this in 2001, this was apparently the best, or at least the machine learning system flavor of the month at that stage. So the idea that they'd started off with decision trees. Then you may have heard about boosted decision trees. So boosting is a method for combining several different classifiers to produce a stronger classifier. A stub is a tree that dies at the root. In other words, if you think a stub is what's left after if you've got a tree and you've pruned it right back to just simply being the root. So essentially, a stub is something which asks only one question, looks at only one feature, and then makes a prediction based on that. However, it's combined in the standard boosting framework so that the actual combined model might actually look at thousands or tens of thousands of features altogether. It turns out it's just actually another method for a linear classifier.
Each stub should be thought of as a feature.
That's right. That's right.
And then it's just the particular estimation.
That's right, yeah. But in fact, actually, the details of the classifier don't really matter. I've got no particular reason to believe that this classifier is doing much better than any other classifier would. And then down here, this is the thing I want to talk about, which is what I've been working on more recently, which essentially is to come up with a tag, a generative model of repairs. And so I'm going to, what that will do is that will give me a probability that a given string is in fact actually a repair. I'm going to have a very simple HMM model, which will then say which will give me an idea of the probability of the string not being a repair. And then the idea is that if the string has a higher probability of being a repair, call it a repair, otherwise say that it's not a repair. That's the generative model. Okay, so now let's actually take a little bit more of a closer look at the structures of repairs. So in general, a repair, this is work that Liz Schreiberg did about 10 years ago now. Classified repairs is consisting of three parts: a reparandum to Boston, an interregnum, which typically consists of fillers like and I mean, can be empty, and then a repair, to Denver. And the repair is often roughly a copy of the referendum. And so one point to note here is that the copy language WW is in fact not a context-free or a finite state language. So if you're going to try to model referenda and repairs, you probably should be looking at a framework which is capable of modeling copies, which is going to take you outside of the context-free framework. On the other hand, repairs are typically very short. So maybe you could say, gee, if I just have a wide enough window, I won't really need to model this stuff generatively at all. And then I should also point out, there are some times when the repairs are not at all copies. In other words, where the referendum is one thing and the repair is really something completely different. And none of the stuff that I'm doing here, I think, really has any hope of capturing those sort of really substantive repairs.
Can you give an example?
I thought somebody would ask about that, and I don't have one.
Well, I wanted to ask you, specifically in context where there's new information that gets prepared away. So, you know, why did the professor teaching this class, why did he go home? Which may be more of a resumption than repair. I'm not familiar with the switchboard treatise to know how they would have annotated that. And I guess my question
I think they would have annotated that as a repair. That's a very interesting one because you've got an anaphor, a pronoun, referring back to a noun phrase which is inside of the repair.
Right. So
Which
casts. Have
casts.
you done any sampling to see how many repairs fall into each of these particular classes? Ones where it's a copy or not a copy.
So I've certainly done sampling to see how many things are copies and not. I don't have those statistics here, but most repairs actually fall into this rough copy idea I was talking about here.
But
That would be an interesting thing to do.
Talked about on the previous slide, will actually detect that, or on this the features.
So very roughly, this method here, if the repair is short and all the features of the repair appear within the window of words that the classifier looks at, this method up here has a pretty good shot of getting it. If the repair is long, but it can be analysed in terms, essentially as kind of like an edit of the referendum, you know, a small number of substitutions, insertions, deletions, or copies, this method here will get it. Right. However, I don't know any method that, I mean, the basic framework will not be able to handle the situation where, because, I mean, the issue you raised is really one of what do you do after you've detected a repair? And the basic framework we're looking at so far is throw it away. Throw the referendum away. And what you're pointing out is, gee, maybe you shouldn't throw it away because you might be able to pick up antecedents from it for an afro. Okay, all right, so the switchboard corpus is about 1 million words long. The annotation includes speech repairs, including the referendum, interregnum, and repair. We've divided into training, development, and test sections. Most of this, all this stuff up here is described in more detail in our NACL 01 paper, 2001 paper. What I'm doing slightly differently here is I've actually deleted all punctuation and partial words ahead of time. So that's actually removing a lot of very powerful cues for us. Then now I'm going to start to tell you a little bit about this classifier which maps each word to either edited or not edited. In other words, it's just a binary classifier. And each word is going to be characterized, each word is characterized by 14 different basic features. But the input to this classifier is a large number of Boolean combinations of these. Actually, I mean, I should point out, these are sort of like attributes which can have many different values, as you'll see. And I look at Boolean combinations of these attribute value pairs, around 5 million of these. The classifier does a greedy feature selection over these, and again, I stopped doing feature selection using cross-validation, and that stops, in this case, at about 4,700 features. So what are the features that I wind up using here? So if this is our typical repair up here, the sorts of features that I would use would be the orthographic word, a Boolean flag that says if you're followed by an identical word, because there's a lot of repairs are just simply the word the, for example, repeated. You know, someone saying the twice. This lets me catch that sort of stuff pretty frequently. Followed by identical part of speech tag, because there's a lot of repairs where you see one noun swapped for another, for example. And then things like the part of speech tags of all of the neighbouring words. These are all features here that are all coming from a repair guesser that I'll say a little bit about, but in fact, part of the reason why I've been looking at the generative model is because I'm really unhappy with the idea of having to have a repair guesser in here. But this is actually worth a fair bit. So on the next slide or two, I'll tell you what the repair guesser is that's used in the 2001 version of the system. But so basically the idea is the repair guesser is going to try to guess whether or not a word is inside of the referendum, and if so, where the interregnum and repair might be that correspond to this referendum. So you're going to have features like the number of words that are in common in the referendum and in the repair. So the higher that number is, the more likely it is that it's a real repair. The number of words in the referendum that don't appear in the repair. These all need to be binned. So I think, in fact, I count in engineer's way, you know, in other words, 0, 1, 2, infinity, right? And then, yeah, other things like this, number of words in the interregnum, number of words at the left edge, I mean, you know, the sort of, and all these features are all found by a lot of very careful playing around with the data, right? And they're nothing terribly principled, nothing really terribly proud of. Okay, so how do I look for these repairs? Well, basically what happens is I work my way incrementally through the string from left to right. At each point in the string, I looked for sequences of words that have identical parse tags. So in other words, I'm going to insist that the part of speech tags. So I'm going to insist that the referendum and repair be the same length, that they have identical part of speech tags, and that the interregnum actually come from known interregnum words. So there really is a very small class of interregnum words. I think something on the order of around 20 or 30. There's no more than that. And so basically, if I can find that, then I'm going to mark these things here as being inside of a referendum. Yeah.
Why are you being so strict about the relation? As you pointed out, there's an edit distance sort of relationship between the referendum and the repair, and there's a very small number of interregna possibilities. So why are you not just looking for the interregna to sort of be the anchor? These are places where I might find it, and being much more generous about basically cutting at that beginning of the repair, sliding back, and looking for places.
The interregna can be empty, so that's one problem. But you're quite right. I mean, in fact, what you'd like is a model which says, gee, I'm really certain that there's an interregnum here, so I ought to be more generous about assigning the repair and referendum.
It was just a complexity issue?
So, well, in the 2001 paper, we also didn't delete partial words or punctuation. And so a lot of the complexity in this, in this component actually was in how one treats partial words and punctuation. Turns out that partial words are a very powerful cue because it's very common for the referendum to end in a partial word. However, I guess it was one of my first conversations with the speech recognition people that told me that there would be absolutely no way that you could expect a speech recognizer to recognize a partial word. So that's one reason why in this version here I've just simply completely deleted this. And in fact, I mean, what I'm about to... So this, as silly as it is, actually works reasonably well. so the baseline classifier is, which maybe says never mark a word as being edited at all, actually gets around 93% correct. So that's roughly because only about 6% of words are actually lie in the referendum. And then this boosting classifier that I just told you about goes up to about 97%. And the thing to really take a look at here is this F-score, which is the geometric average of the precision and the recall. So it's not too bad, but it's certainly not great. And just looking at this stuff by hand, I think that most of the errors seem to be due to the fact that this rough copy detector that I was just telling you about is really way too stringent. This POS identity is too stringent, and many repairs involve insertion and deletion. And so, in fact, what I've been working on is ways essentially of trying to do this rough copy detection in a more principled sort of way. Right. And actually, at last year's ACL Lifetime Achievement talk, Arvind Joshi talked a little bit about how he could use tags to model helical structure dependencies inside of DNA. And it occurred to me that in fact actually that what we're looking at here in speech repairs are much the same sort of dependencies that you get to see in these helical DNA things. So you can sort of imagine what's going on here is that a flight to Boston, to Denver, is that we're seeing a flight to Boston and you start off up here and then all of a sudden the thing curves around back again and then it's as if this whole section here gets excised and then the string continues on from flight to Denver on Friday, right? So in other words, the idea is going to be that we're generating from left to right, but all of a sudden when we get to the repair, we want to sort of actually move down here as well. Does that make sense? So this is just meant to be just a pre-theoretical idea. So the idea is going to be that we're going to generate the referendum and the repair in parallel. So in general, we're going to be generating a pair of words. In this case, it's a pair of identical words too. Then we're going to generate Boston and Denver in parallel, and then we'll decide we're at the end of the repair, and we'll just go on generating these words here in non-repair or normal mode based on the fact that the last word here was Denver. So roughly speaking, the way the model can be described as working is that it's got two modes. It's got a repair and a non-repair mode. And then the repair mode itself has got sub-modes of copy, so this would be a copy here, a substitution, which would be like Boston for Denver, and then you then have insertion and deletion modes as well, which would be where there's a word at one of these levels but not corresponding at the other level. And then the other intuition is that the interregnum is completely unrelated to anything else, which as far as I can tell is right there. Okay, all right. So I hope there's not too many linguists here in the audience, right? Because right now, even though it's a tag grammar, it completely ignores syntactic structure. Instead, and it uses tag substitution to generate the non-repairs in a linear right branching structure, just like an HMM. But it's going to use tag adjunction to generate pairs of words in repairs. One in the referendum, one in the repair. So I'm going to show you the grammar and show you a little derivation in just a moment. But let me just sort of tell you that the non-terminals of the tag can be thought of as like states in this generative process. So if the last word was W and we're in non-repair mode, in general that'll be indicated by the tag expanding a non-terminal of label N sub W, right? If you're generating an interregnum, you're inside of I, and if you're inside of repair mode, up here, for example, you need to know what the last two words were, what your context was. So in repair mode, there's a different state depending on what the last two words. That's indicated by U and V there, okay? All right, I'll try to make this quick because watching derivations is like watching grass grow, right? So imagine we've already processed I want, and so we're now at a state up here which is We've got a non-terminal n want. This says basically I want to now extend, I now want to generate the rest of the sentence after want. The last word was want. I'm going to have a tag rule that says basically, well, okay, you can in fact actually extend in non-repair node the word want by adding the word onto it, and you'll then get into the state non-repair with word right? Does that make sense so far? Cutting to the chase, now let's actually suppose we're now going to insert the word flight. At this stage, we're now deciding that, in fact, we want to start a repair. We're going to start to generate a repair following flight. Okay? So now the structure looks something like this. We've generated our flight here. And there are two extra nodes here that can be worked on. This node down here is where the interregnum is going to appear. How many of you know something about tree adjoining grammar? There's a few of you, right? So tree adjoining grammar has the property that, as well as allowing substitution, which is just like phrase structure rules, which is all we've seen so far, it can also adjoin things, which means in effect to sort of splice things in the middle in here. And the idea is going to be that when we're generating pairs of words in the repair and in the referendum, we're going to splice them on either side of the interregnum here. So here's this previous structure over here, a flight. Okay, now this tag rule over here is a rule that's works with repairs. And so basically what this says is, this is an adjunction rule. It says basically that you can adjoin, this node here can get expanded to include these two bits here, essentially giving us this tree up here. And so what you'll notice has happened is that the 2 has been inserted to the left of the interregnum, and this 2 over here has been inserted to the right of the interregnum. Okay, does that make sense? We're almost done. So if this is our previous structure here, this is the last node that we produced here. This is the 2. And now what we can do is we get another one of these adjunction structures. And now I'm going to actually generate Boston in the referendum and Denver in the repair. So you'll see this is now to Boston, flight to Boston, followed by the interregnum, to Denver. Okay. And then now we're sitting in repair mode, saying that we want a repair whose last referendum word was Boston and whose last repair word is Denver. And so at this stage, this is now where I want to end the repair. So I've got a tag rule that says essentially adjoin this piece of structure in. I'm not going to be generating any more referendum or repair words. Instead, I'm just going to flip back to normal mode. And I'm going to start generating words, just as in an HEMM, as if the last word was the last word in the repair. Okay, so that gets inserted in there. And then finally, I'm not going to step through the rest of the stuff here, but basically generate the referendum underneath of the interregnum, underneath the unfilled interregnum, and then the following words can then get generated off as a right branching structure off to the end over here. So that's the basic idea of the tag grammar. A couple more details and then I'll be basically done. So how might we actually learn such a grammar? I want to learn this grammar from a corpus, of course, and unfortunately the people at Penn, even though Penn is where tag is done, they didn't actually think far enough ahead to actually annotate their switchboard corpus with this particular set of tag analyses, so I can't just read it. It is a pity, isn't it? But you can do something almost close to that. I mean, as I said, they annotated the referendum, interregnum, and repairs in switchboard. So you just used a minimum edit distance method to actually align the referendum and the repair. And actually, for doing that, I also paid attention to part of speech as well. So I had different alignment costs, and it cost less to align two words if they agreed in part of speech than if they didn't. And in fact, I even tried things like, it costs less to align a singular noun with a plural noun than it does to align a noun with a verb, and You know, you can imagine all that sort of stuff. So anyway, what that actually gives me is training data that looks like the stuff at the top up there. In other words, I actually have alignments between the referendum and the repair. So the statistics I'm going to want to learn are things like the following. I want to learn what the probability is. I would just want to learn bigrams in non-repair text. That's easy, we all know how to do that. I want to learn what the probability is of repairs appearing in certain places. So in particular, this PN here is the probability if you're in a non-repair of a repair beginning following this last word. Then PR is the probability if you are in fact actually in a repair, and this is the last word of the referendum, the last word of the repair. You need to estimate what the probability is that the next repair is either going to be a copy, a substitution, an insertion, a deletion, or you might in fact actually end. There might be a non-repair. So that's, I think, also relatively straightforward to estimate. Although there's huge sparse data problems here, and I think even I'm actually using a backed off trigram. I think in fact actually probably the unigram probabilities of these things are probably doing most of the work. And then you need two different distributions down here for predicting the next word in a referendum, given the two previous referendum and repair words, and then the next word in the repair as well. Okay, so these distributions here, I mean, there's sparse data problems here, but at least in principle, there's no problem estimating those from this sort of aligned data up here. Yeah.
So for the first word, you look for the correspondence, but for the second, for the aligned word correspondence, but for the subsequent words, you just ignore the alignment.
Sorry?
I don't understand. It looks like the bottom two probabilities they're not related to each other. So that you're predicting tomorrow on the basis of Boston and Denver, and tomorrow in the referendum, and predicting the repair, but you're not predicting the present.
Maybe in fact it makes sense. The way the model is going to work is that it's actually presenting the referendum and the repair separately. However, maybe I think in fact I'll deal with your question in just a tick. Yeah. So basically, let's just go through how, given those probabilities, how we can come up with the rule probabilities. So if the probability of not generating the word "are" and not generating a repair is just simply the bigram probability of generating "are," followed by the probability of 1 minus the probability of starting a repair at "are." Right? That's pretty straightforward. The probability of starting a repair at flight is just simply the probability of generating flight in the context of the word "are," and then the probability of starting a repair. Not so hard.
Back up one slide, I want to look at the last two probabilities.
So,
The last two, okay, I'll say my question.
yeah, that's right, because I think you're both asking the same question, and I think it comes up right here. Okay, so now imagine that the last referendum and the last repair word is flight. And now I want to generate something which is in copy mode, which means in effect I only need to choose one word, right? What I in fact do is I actually ask, first of all, what's the probability of if knowing I have to generate a repair, what's the probability of generating a copy, right, in this particular context? And then all I do is I just say, okay, let me average the probabilities of generating the word "to" as a referendum word and the probability of generating "to" as a repair word. So
you want to do it that way because it's too difficult to estimate?
yeah,
There's fewer parameters.
yeah,
So
yeah.
these things that you're calling probabilities are not actually marginal
Yeah,
probabilities in the
yeah.
model, they're just numbers.
That's, well, yes,
I
probably.
mean, they're estimated as probabilities.
That's right, that's right.
But
But
they're not actually...
that's right.
Why not look at the probability of 2 and 2 being aligned or Boston and Boston?
Because I think that's pretty rare. So all these things are all backed off themselves tremendously. And all that stuff, I think all these things here all wind up being, is actually, while the back off parameters are all determined automatically, I think they wind up all being backed off essentially to bigrams. Good old-fashioned bigrams, right? So I was just afraid of there not really being enough.
I was going to ask this question later, but
All right.
there's opportunity for it. We'll defer.
All right, okay.
By backing off just at the word level, it seems to me that there's the key intuition that you're missing. Have you considered, for example, running a named entity tagger on the thing and getting the semantic types of these things, or even just monolingual clustering, a la mutual information clustering, or any number of these other things? It seems to me would give you a better smoothing technique that takes into account the relevant piece of information, which is that these things have a relationship to each other.
So that really actually has to do with how one estimates these things. Right. That's quite correct. So right now, I'm not doing any smoothing, not even through part of speech tags or something like that. But presumably that would make a lot of sense to do. I mean, this bit is still work that's ongoing. I think that's a great idea. It's an interesting question because, as I said, what's really going to matter is the relative probability of generating something as a, under the normal mode versus under the repair mode. And so if I improve both probabilities by the same amount, I'm not necessarily going to increase my overall model's performance. I don't know. I mean, I don't know enough about the model.
That last step when you have chosen to substitute, and yet you have multiplied the two probabilities of Boston.
Well, it's because there are two separate words here.
But I thought you said you wanted them to agree on part of speech or...
No, in this model, I'm not. In this model, I'm not enforcing them. I'm not enforcing agreement on part of speech. So perhaps this model ought to. The idea is that if there is part of speech, that there will be a weak part of speech agreement requirement because they're both appearing in similar contexts. Right. But remember, in general, what I'm doing here is I'm actually comparing the probability of a string under this model versus the probability of the string under an HMM, where each word is being generated independently. So basically when the thing is inside of substitute mode, it's generating each word independently, more or less.
Because I thought you might want to do something like probability of the part of speech given to 2 times the probability of Boston given to part of speech better given to part of
So exactly. So what you're saying is that I could do a much more complicated form in here. Yeah.
Not much more.
All those things are all in the eye of the beholder, right? Yeah. And then finally, there's sort of similar models. So for example, if there's the word sitting over here in the referendum, but there's nothing sitting in the repair, then you're inside of delete mode, and then you just pay the probability cost of generating the word inside of the referendum. Similarly, if you're inserting a word, you just pay the probability cost of the word that's being inserted, but you need to be in insert mode. And then finally, there's also a certain probability of you ending completely, which is the probability of switching to non-repair mode. And that's basically it. Finally, in applying this model, I mean, there's several different ways in which you might actually apply it. So one thing that you could do is just simply say, hey, we've got a grammar. Let's just take a tag parser, take a sentence, let's just parse the sentence under the grammar. And find the most likely analysis, and there should be some reparanda and repairs in there, and we'll just take them as being the reparandas and the repairs that we've identified. That involves actually parsing the entire sentence, and this parser is an n to the 4th complexity, not n to the 5th, because we're always only adjoining individual words, but still n to the 4th is still pretty high. And so I would like, if possible, to only have to look at fairly short substrings. I mean, in general, these repairs are never much more than about 4 or 5 words long. So if 5 to the fourth is a much smaller number than 35 to the fourth, for example. So instead, in fact, what I only do is I just look at triples of adjacent substrings, all of which are constrained to be relatively short. And I'm going to be asking the question, what's the probability that this triple of substrings can be analysed as a referendum followed by an interregnum followed by a repair under the tag grammar? And I'm going to divide that by the probability that the concatenation of those substrings could be analysed under the non-repair model. So this gives me the odds that the substrings are in fact actually, referendum, interregnum, and repair. And then I actually have a threshold. If the odds are greater than a threshold, then basically I declare that there's a repair sitting here. If not, I say that there is no repair. This seems more complex, although computationally it's actually less work. It also means that I can adjust this odds ratio in effect to trade precision for recall, and you'll see me doing that in just a tick on the next slide. And then finally, it also handles overlapping repairs, which is something that you find that occurs. Say something like, what does he, what does she want? Where essentially this serves as the repair for this referendum, but it itself is then repaired again over here. So that happens inside of switchboard. And so what would happen is that I can recognize that there's a referendum and a repair here, and then recognize that there's a referendum and a repair here as well. So I can mark both bits as lying in the referendum of some repair. Does that make sense?
You'd be left with nasty pieces where the part of the repair gets consumed by the process.
Although that sort of thing actually really happens. I mean, and the pen people actually annotate the nesting of repairs. So it's, I think it goes down to 2 or 3 levels. So anyway, as I was saying before, one of the things that you can do is, in fact, actually change this repair odds threshold and adjust it to optimize, say, for example, precision or recall. So if you set the odds threshold at 1, you've got very high precision, but it turns out fairly low recall of repairs. If I lower this repair odds threshold, I'm actually finding, in other words, I'm saying that the probability of repair can be lower than the probability of of non-repair in order for me to still count it as a repair. I start to find more and more repairs, but my precision goes down. And optimal performance is somewhere around an odds threshold around 0.1 to 0.2. And that also actually comes pretty close to minimizing the misclassification rate too, which is also kind of nice. So how do we do overall? These are just results that I just came up with last week, so I'm not still completely certain that these are all completely bug-free. In particular, I'm a little surprised. Just a couple of days ago, I put in the results for the boost classifier as well as this other model with different values for the repair odds threshold. It's interesting to see that the boost classifier seems to be doing, unfortunately, sort of 0.74, reasonably much better than this repair odds detector. It's getting 0.7 as an F score. Its precision is much higher, and its recall is basically as good as the repair odds classifier. However, we are sort of comparing apples and oranges here. It turns out that the boost classifier and the tag model were actually trained and tested on different data sets. There's at least 2 data sets sitting on the Penn TreeBank CD-ROM, one of which is got parsed information on it, and the other one which has got part-of-speech information on it. There's much more part-of-speech information, but it also looks as if the parsed information has been hand-corrected. So so in a sense, the boost classifier has got the advantage of working with clean data, and clean data is always extremely valuable. So, as I said, this is still work in progress, but let me give you my conclusions to date. First of all, I think it's worthwhile always remembering that good machine learning techniques are hard to beat. I mean, while I'm always telling students that I think that knowledge-rich approaches are always good things to do. It's also very useful just to take a machine learning method and, particularly if you pick the features reasonably intelligently, it'll often do quite well. And in particular because many of the repairs are just 1 or 2 word repairs, and so they fall within the classifier's local window. It does extremely well. What I'd like to do is to actually take this tag model and use it essentially as the rough copy detector for the boost classifier. That's my intention. And so I'm hoping then I'll get the best of both worlds. I'm hoping then that in fact I'll get the the boost classifier will itself find all of the short range repairs, and then this tag model should actually help it find longer range copy type repairs. Some interesting questions I think are, I think it's interesting that we can find a use for syntactic theories like tree adjoining grammars. It would be interesting if we could actually come up with a way of integrating this sort of model or any sort of model of speech repairs with a tree adjoining grammar in a way that respected syntactic dependencies. So in other words, you could actually use the tag to actually do real syntactic parsing and detect speech errors at the same time. So I think that's actually a very interesting project for some people to think about. And then also, I'm also extremely interested in integrating any sort of, thinking about what sort of models can actually be integrated with speech recognition systems as well. And I think there's still a lot of work to be done there. Thanks very much.
So just when it comes to mind, it seems that in your boost classifier, this notion of using the tag model's prediction opens up a whole space where essentially what you're doing is breaking on the interregnum, sliding things over, looking for someplace where you've got essentially a similarity function of some kind. And there's a whole number of things that one could try, including the thing I suggested before. Another thing that occurs to me is there's a lot of work going on paraphrase recently.
So you're actually saying take a generative model of paraphrase or
Well,
something
I'm just
like that?
wondering whether there might not be some territory to explore there. Certainly all the semantic similarity and clustering sorts of things one should be able to apply, but if these things actually have some sort of phrasal nature to them empirically, you might in fact be able to take advantage of
So phrasal nature they tend not to have. I mean, one of the things that makes them difficult is that repairs often appear smack bang in the middle of a phrase, so at the end of a determiner, someone will decide to back up and repeat the entire verb phrase, so I think that's one of the things that makes them difficult to integrate in with a parser.
It seems like the boost classifier just has a lot more information than the tag guide, just in terms of the part of speech data, which seems to be pretty important. So maybe it's not just that it's a better machine learning technique, but just that it has more information.
Yes, perhaps the thing is that it's, I didn't actually mean that it's a better machine learning technique. What I guess what I meant is that it's a good machine learning approach lets you throw in essentially arbitrary features fairly easily. It's reasonably hard work to integrate more features into a generative model like this. But as I said, one reason why I tried to define things in terms of these probability distributions like this is because this becomes almost like the API to the grammar. If you can come up with better probability distributions here, no matter how they're defined, if they're defined in terms of part of speech tags or semantic similarity or something like that, then at least in principle, automatically, the model ought to get better. But I'm not at that stage yet.
Is there information that you can perhaps glean from parsing research generally that would allow you to predict the kinds of contexts where repairs would happen at points of indecision, which you might model as, high entropy, where people decide to...
I certainly haven't seen anything along those lines. There have been a couple of papers that look at how far the repair is from the beginning of the sentence or the beginning of the last discourse marker, subordinating or coordinating conjunction, those sorts of things. And there are systematic effects there. That probably wouldn't be a bad thing to investigate putting into the boost classifier as another feature, just how far away you are from the start of the sentence. As I said, that's one of the advantages of the machine learning approach, is that it's just easy just to throw it in. Yeah. Yes.
So when you set up your tag grammar, you're not using all the power of tag, obviously. And so the question is whether you could do the same thing using something that doesn't require you to throw a whole tag parser at it.
Well, so first of all, I don't throw a full tag parser at it. It's a specialized, it's a specialized algorithm. But I think it's, you can take a look. It's basically into the fourth because there's 3 string positions that need to be maintained at any one time.
Well, so 3 string positions would give you a cube, right? But
No, because then you iterate over one extra one as you're joining things in. Basically speaking, you need to know here, 1, 2, 3. No, I guess there's 4 string positions.
Oh, yeah, that's right. Right. So I didn't mean a tag parser on the full sentence. I mean, once you've identified the candidate, referendum, interregnum, and repair. That's basically what you're running the tag through. Oh no, that's right. Yeah.
So I do it's a dynamic programming.
Repairs you made right now.
Yeah.
Absolutely not ahead.
But there's a dynamic programming algorithm underneath that does that. So I think in terms of the simpler tag formalisms, there's one that Yves Chabès came up with, but that's only got context-free generative power, for example. So that won't be able to come up with the copy constructions. So you need something which has got generative power that's trans-context free.
That's certainly true, yeah. I just would have formulated it differently, and I'll ask you afterwards what the way I would formulate it as well.
Yeah.
A lot of this could be kind of moved if you could put prosody into it. Because after all, there's a lot of information in the 2 states. Right now, for example, when you look at these 4 points, you think this is an interregnum, but I'm sure the acoustics of that are very good.
I think it would be very useful to try.
I don't quite know what
So let me go out on a limb. I actually think that the generative model that's based on the tag actually has some prospects for being extended to working off lattices. Because just like all the context-free and parsing methods, which only really care about, pairs of vertices, this thing only cares about essentially quadruples of vertices and systematic ways for extending them over arcs. So computationally, we might have to find all kinds of heuristics or best first search methods or something like that. But I think this general framework ought to be useful for finding likely repeated, common sequences inside of lattices. And so and there, presumably, we could try to incorporate prosodic information as well.
If you wanted to do a simple experiment, I think it's not much, but a portion of the switchboard tree bank is resolved here. And it has things like
That's true.
false breaks up to I think 3 levels.
That's true. Yeah.
And
Yeah.
some problems.
That's true. Yeah. So at this stage, I'm really trying to think what's one of the simplest improvements to this component of the model, which will give me the biggest bang for the buck, right?
Actually, when you said this was like an API to the grammar, I was going to say that actually this is not quite the API you want, because you definitely want the PR and the RR to be a joint model. And sort of...
What, these 2 things to be a joint model? Yeah.
And conditioned on the little m event. So that you will in fact, I think you end up using the same model for the insertions, deletions, and the
That's right.
solutions, but in principle you want them to be conditioned on the event little m in the model.
Yeah. I think I'm just so short of training data. I mean,
No, then
Well, but the API should say that there's a joint distribution, and
Right.
then if you want to estimate it in some nutsy way,
Right.
with
Right.
your parameters and
Right.
what
yeah. I was just trying to make that as simple as possible. Yeah.
In this model, I didn't see where you use the information of interregnum. Did you use, are you using any information of interregnum?
I didn't in fact go through that in a great deal of data, but it turns out that there's only very few words which can possibly appear as the interregnum. So, in fact, I don't smooth the interregnum subtree probabilities at all. In fact, it's as if there's basically a little PCFG that only generates interregnum, and it will not generate anything other than these interregna strings. So what that actually means is that, and it generates these sorts of strings with very high probability. It will generate epsilon, the empty string, with a reasonably low probability. So that this actually means that this entire tree is going to have fairly high probability if this interregnum here is actually located over some lexical material, and will have fairly low probability if the interregnum is not. So in other words, that's one way where the interregnum actually makes the whole repair analysis much more likely. Does that make sense?
Yeah, so do you mean that if you observe this interregnum, then you get a higher probability for predicting the repair?
That's right. The entire tree structure's probability is the product of the probabilities of all the components.
So it's really not into the fourth because you don't have to go with every position that you can. In fact, you research around.
Well, no, there are also repairs that have null interregna. So there's...
You have to send every null. But then that collapses two of your four.
Oh, I see what you... So you're saying, in fact, that I could prune.
Null is
So you're saying what I could do is I could, in fact, actually prune. I could either say basically either the interregnum is empty, or it must be the maximal sequence of these guys. Yeah. I don't do that.
I mean, if you were to do interregnum detection, that probably would
That's
be
right.
pretty high probability, right?
That's right.
You still have to consider all the epsilons, but that would
That's right. That's right. No, that's a very good idea. That would probably cut down on it. I mean, I also wind up pruning all this stuff too. I mean, in the dynamic programming. So I must admit I don't know how much additional work I'm doing there, but that's a good suggestion. Thank you.
I have one last little question.
Sure.
About the nested repairs. Is there a difference between the boost classifier and this one? Is this any better?
On nested repairs, I just haven't done those. I haven't done those experiments on
I
nested
wonder if
repairs.
this is actually better than the boost.
Actually, one of the things that I did in the boost, part of the difference between the state of research I'm at with this tag classifier and the boost classifier is that in the boost classifier, I actually looked at the word-by-word decisions, and I also had additional fix-up rules that would sort of say, gee, if this word is predicted to be edited, this next word is non-edited, and the next word is edited again, maybe fill in smooth over the edits, right? I just had those as additional fix-up rules that would come in and, because typically edits, repairs come in long blocks. You don't find, non-referendum word, referendum word, non-referendum word, referendum. They don't zigzag backwards and forwards. So that's one of the things that the output of the boost classifier has essentially as a heuristic, just applying to it. All right.